Hi, I'm Tim Doria from Boston Decision. Today we're going to show how to build a document classifier in under 25 minutes using the R programming language. Now the way this will work is as follows. We'd like to give a document to some type of machine learning algorithm or some piece of software we're about to develop, and then have it score or assess who is the author of that piece of text. Now, while this has clear applications to brand management and things like plagiarism detection, we can easily substitute in the text and the item that we're looking to classify or predict and make this a lot more extensible. For example, say if we were to feed in invoices where we have service description text on the invoice, we can use this to detect if there might be a case of fraud where a person's getting charged for a service that was never rendered. Or we could use it to detect situations where we might be getting overcharged or undercharged for a given service. Alternatively, we can use electronic medical record data. For example, the physician narrative, the free-form text that a physician enters in when they're seeing a patient. We can then use this to detect, hey, did the physician provide quality care? Did they do or take each of the steps that they were expected to take given the nature of the patient's illness? We could also use this to detect or predict the cost of that patient in terms of their health care over the next 5-10 years, or whether or not that patient's likely to observe a chronic illness over the next 5 to 10 years. These are the types of things made possible by this technology. Now for today we're going to be looking at speeches and analyzing the text to determine who spoke them, whether it be Obama or Romney, given that the 2012 campaigns are upon us. These are the sources. We have 25 minutes to do this. Here we go. Okay, so to develop our document classifier, we're going to be using the R programming language, which is free and open source, and we're also going to be using RStudio, which is an R development environment. Let's first take a look at the data. So what I've done is created two directories on my hard drive here within my speeches folder. Each directory has a speech, one speech per file. And so let's just open up a speech, and you can see it's free-flowing text. All right, same thing for Obama. Okay. So let's go ahead and create a new script. And what I like doing before I start a project is writing what's called pseudocode, which is kind of a plan of attack, what I plan on doing in the code. So the first thing I'm going to do in this code is I want to initialize my environment. So what are the libraries, the directories I'm going to be using, things of that nature. Then I want to create a function that will clean the text, because text is inherently dirty, so a lot of it has to get cleaned out. Might as well do a function since I have to apply it to two different or multiple candidates. Next, I'm going to build what's called a term document matrix. This is where the magic happens, where we're converting text into a quantitative format that we can then analyze. I'm then going to take this term document matrix, or rather two of them, one for each candidate, and just attach the candidate's name to the term document matrix. And then what I'm going to do is take each of these two matrices and stack them one on top of the other, because we're going to feed it all in at one time into our model. We're going to create a holdout sample. This is a good practice in data mining. And what happens is we take a portion of the speeches and we use it to train the model or build the model. It will learn from these speeches the patterns between the speech, the text, and the classification, or in this case the name of the candidate. And a small subset of those speeches, we're not going to tell it who said the speech. This is our holdout sample, and what we do is we use it to assess how well the model works. So it will make predictions on this holdout sample where we're not telling it who said the speech, and we'll compare those predictions to who actually said it to give us a measure of how accurate this model is. Okay, so we're then going to do the model, the algorithm. In this case, it's called k-nearest neighbor is what we're going to be using in terms of methodology. And then we're going to assess the accuracy. Okay, so let's go ahead and start doing this. So since the initialization is pretty straightforward, I'm just going to copy and paste what I'm going to do here for the initialization. Okay, so what I'm doing is I'm simply loading in the libraries that I intend to use functions from. So the text miner library plier. R has a bunch of libraries that extend its functionality. And I'm simply looping through these to load them up. I'm setting an option here, strings as factors equals false. When you read text data into R, it occasionally likes to convert it from text or string or character into kind of nominal or categorical variables. We don't want it to do that here. We want to keep them as is. And then what we're doing is we're just specifying the names of the directories that's from here, these subdirectory names here, and then the path to get to these two subdirectories. Okay, so now let's go ahead and start writing a function to clean our corpus. Now, what is a corpus? A corpus is simply a collection of documents. So what I'm going to do is just create a corpus for each candidate and then take all their speeches, all their documents, and incorporate them in one candidate per corpus. We do our operations, a lot of our cleanup at the corpus level. We apply our functions, cleanup functions, across all speeches or all text within a corpus, and so that's one of the reasons why we create this construct. So I'm going to go ahead and call this a function, and we're going to pass in a corpus. And what I'm going to do is just apply a variety of cleanup functions that are available within TextMiner. So let me go ahead and I'm just going to bring them in since they're fairly straightforward and they're consistent. So we're going to remove punctuation, white space, we're going to convert things to lowercase, and then we're going to remove parts of speech that really don't have all too much meaning, such as articles and things of that nature. We call these stop words. They really don't help us to identify the speaker of a particular speech or classify a document. After we do this cleanup, we're going to return the result, which in this case is corpus temporary. Okay, so we've cleaned our corpus. The next step is building the term document matrix. And what I'm going to do is, since we're going to do this for both candidates, I'm also going to wrap this into a function. So generate term document matrix. This is going to be a function where we're going to pass it the name of the candidate and the path. Okay. So what I'm going to do, the first step here is I want to take one of these candidate names and then the path, and effectively put that candidate name at the end here so we could point to the directory that the speeches are found in. So to do that, I'm going to just create a speech directory variable, and I'm going to print those two variables together as strings. So what I mean by that is I'm literally going to concatenate the path with the candidate name. And we're going to set that equal to the speech directory, S directory. Okay, so the next thing I want to do is create a corpus based on this one path. This whole path here and all the documents inside of it are going to become a corpus. So to do that, we're going to call the corpus function, and we're going to be using a directory source, since we're using a file directory, whereby the directory is going to be equal to our ester that we just set up. And the encoding for the text is going to be ANSI. ANSI encoding. Alright, so that looks good. The next step is we want to apply our cleanup function. So this is the clean corpus. We're going to apply it to the corpus that we just created. And after we do the cleanup, we're going to create our term document matrix, whereby each term that appears across all of our speeches is going to appear on one axis, and then the document that appears in is going to appear on the other axis. Okay, this is really just quantifying the text. So call the term document matrix function, and we're going to feed in the clean corpus. Okay, so now we have our term document matrix. The next step is we want to remove sparse terms. These are terms or words that appear infrequently across speeches and really don't give us much value, or at least in this case we found that it didn't add much value, just slowed down the analysis. And so we're going to go ahead and remove sparse terms and set up a parameter here for an acceptable level of sparseness. And finally, we're going to return the result. And the way we're going to return the result is as a list, where the first item in the list is going to be the name of the candidate, and the second item is going to be the term document matrix that we're calling TDM, and we're outputting the result. Okay, so let's actually go ahead and run what we've done so far. So I'm just going to create a variable for the results, and I'm just going to loop through the two candidates and apply the generate TDM function that we wrote to each of the candidates, and we're going to pass the path name through to the generate TDM function. So the path name comes from here. Okay, so let's go ahead and run everything up to this point. Okay, we can see it's running right now. And this is a fairly old machine, about 6 years old, so it's not a hardcore heavy-duty machine, and we're analyzing about 70 documents. Okay, it's done. We see we got some warnings. Let's just take a look at the warnings. Okay, these aren't bad. What this means is that the last row of the text documents should generally be blank, but it says that the text goes down to the bottom. That's not going to impact anything. So now let's just take a quick look at our result. And we can see it's a list variable. It contains two items, two elements, each of which are also lists. And each item in that list is the name of the candidate. So we see Romney is here. Second one is Obama. And then we have this term document matrix that is in as the second element of each of these lists. Okay, so now let's do a little bit of cleanup here just to get our matrices ready for analysis. So what I'm going to do is append the name of the candidate to the term document matrix. To do that, I'm going to create another function. I'm going to call bind candidate to TDM, and this is also a function where we're going to pass it each of the term document matrices. Okay, so what I'm going to do first is I want to convert the term document matrix into a numeric data matrix. And I'm also going to transpose the row and column variables to make it easier. I want to have each term, or rather each speech as a row and each term as a column. And right now it's the other way around. So I'm going to do a matrix, data matrix. I'm going to put in term document matrix. And remember, this is a list, so we want the second element, the term document matrix element. Okay. Next step is I want to convert this matrix into a data frame. Data frames provide some additional options such as cbind, where we can bind additional variables in. It's a little bit easier to work with for what we're doing, so I'm just going to do that conversion quickly. And I like adding strings as factors in. Equals false, just to protect myself in case I forgot to put it up above. Okay, so what we have at this point is we have a data frame. Think of it as a spreadsheet where each speech is on a row, and then each variable name, each term is on a column, and then the cells contain the frequency that that term appears in that speech. What I want to do now is in the last column, I want to put the name of the candidate who said the speech. And so to do that, I'm going to be using the cbind, column bind is what that represents. I'm going to take the speech data frame, and what I want to do is replicate the name of the candidate, the number for the number of rows that we have in our matrix. Okay, so what I'm doing is this matrix has a certain number, or rather this data frame at this point has a certain number of rows. So what I'm doing is I'm creating a new variable that's going to be populated. Every row is going to be populated with the name of the candidate, and we're simply going to be repeating that the same number of rows as the data frame already has. So this just means that the last row is going to be completely filled, and every row is going to have the name of the candidate. That's what this is doing. And then what we're going to do is just set the name of that last column so that we understand what it is. So in order to figure out what the last column is, I'm just going to do a simple count here, number of columns in df, and whatever the number of columns is, whatever that last column, we're going to just name this target candidate. Okay, and then we're going to return the result. Let's run that function. I'm going to use lapply to loop through both term document matrices. and I'm going to run the function we just created, bind candidate to TDM. Okay. Okay, let's try that again. Okay, done. Let's just take a quick look here. Okay, so you can see, so we have a data frame, or list of two data frames, 32 observations. Those are the speeches, and then we have variables here. And these are just the names, the terms. And here's the second one here, data frame with 34 speeches and 298 terms that appear across the speeches. And then here are the frequency counts. Okay. So now what we want to do is we want to stack the two, because remember we have two data frames now. What we want to do is just stack them together. So I'm going to do TDM stack. I'm going to use do call rbind fill from the plier package, and I'm going to apply the TDMs. So this is just row binding them, or I binding them, and then because they might have different terms, each one of these data frames, it's going to fill in an NA wherever there's a term in one that doesn't appear in the other. And we don't really want an NA, we just want a 0 here because it just means that that term didn't appear in a particular speech. So I'm going to do TM stack. If we see an NA anywhere in the result, we're going to set that NA equal to 0. Alright, so let's go ahead and apply this. Okay. Let's just take a head. Okay, so you can start seeing what this looks like. Again, every row represents a speech. We now have all the speeches for both candidates added together, and then every column represents a term that has appeared in one or more of the speeches. And let's actually just see the number of rows here. It should be equal to the total number of speeches across the candidates. So TDM stack. So we have 66 total speeches. And let's actually see how many terms we have. 492 terms across all the speeches. Okay, so the next step is to create our holdout sample here. So the way we do this is I'll just create a training index. These are going to be the rows that we're going to teach the model. Okay, so I'm going to take a sample, and let's just do nrow TDM stack. Okay, so I'm taking a sampling of the number of rows in the result in the data frame that we're currently looking at, and I'm going to round off ceiling multiplication of the number of rows in the result times 0.7. So I just want to take 70% of the rows and then use that to train the model. Then we're going to test the model using the remaining rows that weren't used to train it. Okay. And the way that we can note the ones that weren't already used is we simply do negative train.tdx. Let's try that again. Okay. And let's just see what this looks like. See, so that's a sampling. These are just a random sampling of speeches that will be used for testing, and then here are speeches that will be used for training. Okay, and it's randomly sampled. We're going to pull out the name of the candidate and set it aside in a separate variable. So what I'm going to do is just create a new variable I'm going to call TDM candidate. And this is going to be TDM stack, our data set that we're currently working with. And what we want to do is include in all rows but just the column target candidate. And I also want to create another variable that will have all of the columns except for the target candidate. So this one will have just the target candidate column. This one will have all of them except for the target candidate. So the way I'm going to do that, ddm stack okay, so we want to incorporate all the rows, but we don't want to include the columns that are in target candidate. So this has the effect of including all rows not in the target candidate vector, which is a vector of 1. So everything except target candidate, all columns except for target candidate are going to be in there. Okay, so let's actually do our model now. So we're going to create a new variable called knn prediction, where we're going to run a k-nearest neighbor algorithm. And what we're going to do is feed it in our training data set that doesn't have the names of the candidates who said the speeches. And let me just make a correction here. We only want to include in the rows where we've decided that row is going to be training data. Okay. Then we're going to put in the test data and only include in those rows that are for testing purposes. And finally, we're going to give it the names of the candidates for just the training set. This is where it's going to be learning, not the testing, just the training set. And finally, okay, so I think that's what we're going to be doing, is running k-nearest neighbor algorithm. We're giving it the rows that it's going to be learning from without the name of the candidate. We're giving it the rows that we're going to be testing on without the name of the candidate. And here we're giving it the names of the candidate that said the speech for that training data that we've provided in the first argument here. All right, so let's go ahead and run the model. You can see how fast, microseconds. Okay, so let's now go ahead and see the accuracy of our model. One way of doing that is setting up what's called a confusion matrix. A confusion matrix shows how our model predicted on that test set against speeches or documents that it didn't know who said or what the classification was. And it compares the prediction to what we actually know, who we actually know said the speeches, or how we know the documents should have actually been classified. And so what we're going to do is set up a table where we're going to label one axis as predictions, and we're going to set the predictions equal to the results from our k-nearest neighbor output, and then the actual results, the actual speakers of these speeches, is going to be the TDM candidate name for our test set. Okay, because remember, what the model is doing is it's making predictions on the test set. So what we're doing is we're labeling the predictions as predictions, and the actual results are the names of the candidates that were fed into the test set. So let's go ahead and run this. And let's go down here and let's actually take a look at what the confusion matrix looks like. Okay. So the way to interpret this confusion matrix is here on the left side are the predictions made by the model. So the model said that 13 of the documents were spoken by Obama. And on the top here we see the actual. So out of those 13 that the model predicted were spoken by Obama, all 13 were indeed spoken by Obama. Same thing with Romney. With Romney, our model predicted 6 of the speeches were spoken by Romney. And for each of those 6 speeches, Romney was indeed the speaker. And so we can go ahead and calculate accuracy. I think it's fairly obvious already what the value would be. Let's go ahead, though, and show the formula for how to do that. So accuracy would simply be the sum of the diagonal of the confusion matrix divided by the length, or the number of test speeches that we plugged into the model. And we can multiply this by 100 to to give a value that is expressed as a percentage. And let me just clean that up. Let's go ahead and run this. I always make the mistake. Let's type in test instead of text. We're going to click run, and sure enough, we see 100% accuracy. So within the last few minutes, we were able to develop an entire system that will take in a speech, make a prediction, output that prediction, and get very high accuracy based on analysis of text. So this is a document classifier system. For more information, feel free to visit www.bostondecision.com. Look forward to talking. Take care.